We're moving on to a new topic, but the segue is really natural. We were talking about sums, and now we're segueing into recurrence equations, which are usually solved by coming up with some sums that we have to manipulate, and how it relates to recursion and induction, mathematical induction that you learned so far, and recursion that you learned last month. So we're going to move into this slowly. There's one little topic that will come up today that really belongs in the last problem set, and that's geometric series and variations of geometric series. You'll see that in about 15 minutes. There's one problem on the last piece set that you need to know how to do that for, and you can hand that in today if you haven't done that yet, in case you were waiting for me to do it. So we'll do that soon. Okay. The way we're going to begin on recurrence equations is to start off with the simplest recurrence equation I can possibly think of, and also maybe the most common one you'd see in your day-to-day goings-on in life. And that is, you put some money in the bank and you get some interest back on it. Okay, so say you have $100 and you put it in the bank and they promise they'll give you 10% interest at the end of the year. So at the end of the year you get $110. Okay? And you can take it out and leave, or you can let your money ride, go for another year, right? And they'll give you another 10%. So let's write this out in math talk. Here's the amount of money you have after a certain number of years. We'll call it money. Money 0 is how much money you have after 0 years. And let's say that's $100. And money 1, assuming it's 10%, is going to be $110. How much do you have after the second year? Just to make sure everybody gets this. $121, right? You don't just get another 10, you get 10% of this. 10% of this is 11, so you get 121. In general, if you want to know how much money you have in the ith year, you can write that down with respect to how much money you had in the bank after the year before. In particular, it's everything you had the year before plus 10% of what you had the year before. And you get that by multiplying by 1 for what you had before, plus 0.1, plus 10%. So 1.1 times mi minus 1. That's a recurrence equation. It's an equation that tells you the value of something in terms of itself on a smaller index. It's just like recursion. Every time you write a recursive program using recursion, you say, I'm going to do this program, and in the third step, I'm going to do the program again for a smaller input. Okay, so a recurrence equation is a mathematical form of recursion in some ways. And a lot of recurrence equations end up being equations representing how many steps your algorithms are going to take. So if you have an algorithm that calls itself and you want to figure out what's the time complexity of this algorithm, it'll end up being a recurrence equation, and you have to learn to solve that recurrence equation in order to figure out the time complexity of that algorithm. And that's probably the place where recurrence equations show up the most in computer science, is in analyzing algorithms. Okay, questions so far? So here's the way a recurrence equation usually looks. It gives you the relationship between one case and some other smaller cases, and it gives you a base case. So let's solve this so that instead of this recurrence relationship, we get what sometimes people call a closed form. A formula here that just has I in it, that doesn't have any dots. I won't define rigorously what a closed form is, but it basically means something that you can just plug in the number and compute quickly without having to worry about loops or computation or anything. So some of you probably can see what this is, but what I want to do is pedantically go through a method which will be useful when it isn't so obvious to see what the answer is here. So here's one method, and it's a brute force method of solving recurrence equations, and it will help you solve a lot of recurrence equations, but when they get complicated, this method will break down and we'll need some fancier techniques. And later on, a couple lectures down the line, I'll show you some fancier techniques. And I should mention in advance, recurrence equations are from discrete math. The continuous version of a recurrence equation is a differential equation. Okay, differential equations are like continuous recurrence equations to some extent. And a lot of the techniques that you can use in differential equations, you borrow for recurrence equations. So with that said, those of you who have taken differential equations and maybe hated it, recurrence equations aren't anywhere near as bad. They are discrete, and you can usually get a better sense of what's going on without just mysteriously following rules. So that's what we're going to do right now. We're not going to mysteriously follow a rule. We're just going to logically figure out what the solution is. And here's how we do it. We know that this relationship is true. So what we're going to do is we want to get rid of this m on this side and just get something like an I squared, something with a formula there. So if we want to get rid of this, we'll just figure out what it equals and substitute for it. Well, what does mi minus 1 equal? Well, the good thing about a recurrence equation is that it tells us what m of anything equals. mi equals 1.1 mi minus 1, so mi minus 1 equals 1.1 mi minus 2. Okay, in place of I put I minus 1, so I minus 1 minus 1 is I minus 2. And now I take this. My whole goal was to get rid of this m, and now I put this back here. And here's what I get as my result, which I'll circle. mi equals 1.1 times 1.1 squared times mi minus 2. All right. Who gets that process? Everybody with me? All right. See, yeah. Anybody have a question? Everybody's okay. Good. Sharon, question?
Yeah. I just missed that last step. You just substituted back. Oh, I just see that.
So in place of mi minus 1, we get 1.1 mi minus 2. So I get 1.1 mi minus 2. That's 1.1 squared. So what if I did this again, the whole process again? Get rid of mi minus 2 and put it back in there. What does this look like the next time? Right. But we're going to leave it as 1.1 cubed because what we really want to do is see a pattern. What if I do it r times? I do it as many times as I like. Because you really want to get rid of this, right? I mean, what am I doing? I still have this m here. Goodbye. I want to get rid of it. Bye-bye. When can I get rid of it? When it's m0, when I hit the base case. So I want to do this as many times until the base case shows up. So let's see what happens when I do it r times. When I do it r times, I get 1.1 to the r times mi minus r. And what should r be so that that mi minus r becomes m0? R should be equal to I. So if I do it I times, let r equal I, then I get m
equals 1.1 to the
mi equals 1.1 to the I times m0, which is 100. So there's a formula for how much money I have after the ith year. And that's why if you go talk to some financial investor who memorizes some of these numbers in their heads, if you figure 10% a year, which is what the stock market's been doing for the last 50 years on the average per year, more or less, and you're going to leave your money in long term, then how long does it take for 1.1 to the I to end up being 2? That means your money's doubled. And they like to tell you when your money's doubled because it makes you feel good. Yeah, so between 7 and 8 years, something like that. 1.1 to the 7 something ends up being 2. And it's a good thing to keep in mind. 1.1 squared is about 1.2. Square that again. 1.4, square that again. 1.96. So it's more or less 8 years.
You can also do the rule 72. 72 divided by the interest rate is how long it takes to double. So like if your interest rate is 9%, it'll take 8 years.
So it's a good approximation. Good. All right, well, that's a formula about interest. You might remember this from 2 months ago when I was introducing the letter E, or the number E, right? And we cut this down. We did it every half year, every month, every day, every second. And then out of that came this very complicated formula for E that had a limit involved in it. We're not going to go down that direction today, but it should remind you of that. This is just a simple recurrence equation. We solved it by the method I call repeated substitution. It's just a logical method. Follow it to the end. You almost always get some success. But when the recurrence equation is a little bit uglier, you got to get fancier techniques or you got to give up on this completely. All right, questions so far?
If you did take this to the exponential, to this continuous interest, that then is no longer a discrete problem? Or could it still be?
No, if you take it and and you compound it, say, every moment, then it becomes a continuous problem. Right. Right. Then it's no longer discrete. Let's do another problem like this, set up a recurrence equation, but this time the problem we'll do is an algorithm that all of you probably know, and we'll create a recurrence equation that's the time complexity of the algorithm, how many steps it takes in order to solve the algorithm. We'll solve the recurrence equation by the same method, and then we'll move on to Towers of Hanoi, which you've seen before and which is a classic example of recursion. It will take us to the next stage. All right, so the next example is sometimes called binary search. And I like to just think of it as a game you play with kids. So I'm thinking of a number, you have to guess the number, and you're allowed to ask me a question, make a guess, say 7, and I have to tell you whether it's, higher or lower than my secret number. Okay? That's equivalent to if I give you a list of names in a big long array and they're all sorted and you want to find a particular name, you go into the center of that list and you check if the name that you're looking for is bigger than or smaller than the name in the center of my list. And depending on the answer, you go to the right half of the list or the left half of the list. So we're going to do this with numbers. All right, so everybody knows how to play, right? If I pick a number from 1 to 10, you're going to guess 5, and if I say it's too big, you're going to guess, right, halfway between the other. All right, so let's analyze this algorithm. We're not going to write it out in Scheme. You could write it if you wanted to, but let's analyze it. How long does it take? We'll say Tn is the amount of time it takes if you have the biggest number being n, or the length of your array is n. So every time I make a guess, I'm going to do binary search on a smaller problem. How small is the problem that I do it on the next time? Half the size. And let's not worry too much about whether it's even or odd, because it'll just make the analysis a little ugly. We'll approximate n over 2. Okay. How many steps does it take before I can turn this into a problem where the recursion works on half the size? What do I have to do? I have to ask one question and get an answer, right? One step, we'll call that. So here's the recurrence equation. 1 plus t n divided by 2. And how long does it take me to solve this problem if the person says, I'm thinking of a number between 1 and 1?
0 steps.
Yeah, or 0 steps. You don't even have to guess, because we just believe everybody can. I'm thinking of between 1 and 1. Do you all know what it is?
Can you give us a clue?
All right, so T1 is 0, and here's the recurrence equation for any other n. Why did I use n this time instead of I? It doesn't matter what letter you use. Don't use 17. Use a letter. All right. Let's solve this the same way we did before. But this time, it won't be quite as simple, but almost as simple. The next time it'll be a little more complicated, and the time after that a little bit more, until we say, whoa, this method isn't working, and we come up with some new methods. All right. The method before works like this. We want to get rid of Tn over 2, so we write that underneath here, and that equals 1 plus
Tn over 4.
n over 2 takes the place of n, so it becomes t half of n over 2 is n over 4. And if we take this and substitute back in there, we get Tn equals 1 plus Tn over 4. Okay? Now we're going to do this a whole bunch more times. Say I do it r times. Instead of writing 4 here, I could write 2 squared, and that might give you a hint. Every time I do it, this exponent here pops up by 1. Every time I do it, it gets multiplied by a factor of 2. So the exponent goes up by 1, and I get an extra 1 here in the sum. So what does it look like when I do it r times? R plus t and again, I want to get this down until it's a base case. So I get to choose how many times I want to do it until I hit that base case. And that means I want this n divided by 2r to equal what? To equal 1, because that's my base case. All right, so that means n has to equal 2 to the r, and r has to be log base 2 of n. For me to get rid of this t on the right side, I need to do this as many times as the log base 2 of n. So if my n started out 64, I need to do this 6 times. 64 to 32 to 16 to 8 to 4 to 2 to 1. If I do it that many times, and then I see what I get here, I get t sub n equals log base 2 of n plus t of 1, and t of 1 is equal to 0. So here's my closed form solution for this recurrence equation. And we say that binary search is a big theta log n algorithm. It's a very fast algorithm. All right, questions about this?
Is that the best search?
I don't think you're going to do better if you don't have any other information about the stuff you're searching through. Yeah. We aspire to this, yes.
Why isn't the answer an absolute yes? And if you're searching from 1 to 1024, you can't do better than doing it in 10 steps.
We can't.
You can do better than
You can't, unless you know something else about the numbers, unless you have some more information. Yeah.
How did we get the n over 2 to the r equals 1?
Because I want this index here to turn into a 1 so I can get rid of it.
Okay.
So I have choice over r. R is how many times I do this iterative repeated substitution. And I'm just going to want to figure out what r should be so that n divided by 2r turns into a 1.
Okay.
So I set it to 1 and I calculated what r should be. So I chose this because I want to do it that many times until t1 shows up. Does that make sense? Okay. Other questions? Here's a baby toy. This puzzle has some kind of legend or folklore associated with it. You know, that some group of monks were hanging around in a basement and found a secret piece of paper, and the secret piece of paper described this puzzle, and it said there's 64 of these donuts on a big post, and if you follow the rules and transfer them all from this post to this post, then some great apocalyptic vision will blah, blah, blah. It's just a made-up folklore, and it's a fun story, but I don't think this puzzle is actually more than 100 years old, in fact, and I don't think anybody really knows the real origin of it, but I think as far back as anybody has tracked it, it only goes back 100 years. And here's the puzzle. The puzzle is you want to move this set of donuts from here, say, to here. And there's a middle spot in between that I can use to help me. And the rule is I can't just pick up all 4 things. I can only move one at a time. And I'm not allowed to put bigger ones on top of smaller ones. Only smaller ones can go on top of bigger ones. I'm just fooling around. Those are legal moves in this puzzle. So how do we move all these 4 from here to here doing those rules? You can get lost in the jungle of solving this puzzle, especially if you had 64 donuts, and not have any idea where you are. But if you organize your thoughts recursively, this becomes a 3-line program. And all the details are behind the scenes in the recursive stack that your program does for you. And that's why it's such a classic example of recursion. So I think you've all seen this example before, but I'm going to review the recursive solution, write it up in pseudocode on the board. We'll do a couple examples, make sure everybody gets it. Then we're going to analyze its time complexity, see how long it takes. A geometric series is going to show up. So that's when I'll show you how to solve geometric series and versions of them. And then we're going to discuss possible variations. And I'm going to show you a graph of this picture, a graph of the computation, which will give you a bird's eye view and an understanding of the problem that most people never get from just thinking about the recursion. And that will show you the power of graphs, how graphs sometimes give you exactly that, an incredible perspective on a problem that you otherwise miss completely. All right, so that's our plan, and the first step is reviewing this algorithm.
What is pseudocode?
Pseudocode means it's not in any real language, but if you know any language, you could probably turn it into that real language. It'll be kind of a halfway Lisp, halfway C kind of code. All right, so here's the method. The method is I want to move all these 4 to here. Then recursively, I'm going to do a problem on 3 donuts. Okay? This is my leap of faith recursion. I'm going to assume I could do the problem on a smaller set. So I ask my recursive slave, do me a favor, take these 3 and do the problem, but don't move them from here to here using the middle. Move them from here to the middle using this as your auxiliary. And there's no problem doing this, right? Because this guy might as well be nailed to the bottom. We're not going to get any illegal moves because we left this guy in the bottom. Maybe I don't need to mention that. Maybe that's obvious. But when I give you the problem set, I'm going to give you variations of how Fruity Freddy and Ditzy Dotsy tried to come up with variations of this puzzle. And they come up with phony baloney recursive algorithms that look right. And part of the reason they're wrong is because subtle assumptions that I might miss to mention now because they're obvious don't apply to the ones that they came up with. So be careful. It's a little subtle why things always work. So this works because this doesn't affect anything having this big guy in the bottom. And I can do this 3 problem just like before, but I'm going to end them up here. So I'll just reverse which one I'm going to and which one I'm using in my list of parameters. You'll see this on the board in a second. Then I take a single move. I move the big guy over here where I want it to be. And then I again do a recursive problem on these 3, moving them from the middle peg to the 2 peg using the original from peg. And that solves the problem. 3 steps, 2 recursive calls, 1 actual move. And the base case here is if you ever get down to having no disks on a peg, then I don't do anything. That's an easy base case. Watch. I'm going to do this one recursively. I take off the top, and there's none on the top, right? There's only 1 on the bottom, there's none on the top. So what do I do with none? Recursive call, don't do anything. Now I do the middle step. Move this from here to here. Okay? Then I take the empty pile that I had moved here, and I move it from here to here. Now I'm done. In other words, the base case really is an empty disk. You don't have to make the base case a single disk. You can make it an empty disk, no donuts at all. An empty peg, no donuts. So I'm going to write this algorithm up on the board now, and then we're going to analyze it a little. Here's what it looks like. I'll call it TOH for Towers of Hanoi. And Towers of Hanoi has how many parameters? The number of the donuts or disks, and not just the number of the pegs. Well, we're assuming there's 3 pegs in this one. Right. Where I'm moving from and where I'm moving to, and which one is going to be my auxiliary one. Okay, so presumably these have real names, called A, B, and C. And A might be the original from peg, B might be the original auxiliary peg, C might be the original to peg. But as I move around from, to, and auxiliary, I'm going to change values. Changing from might end up being C later on, etc. So that's why we need these variables. So here's what it looks like. Towers of Hanoi, we'll call it N, from, to, using. Those are the 4 parameters. This stores the name of a peg, this stores the name of a peg, this stores the name of a peg. Okay, they're variables that store the name of pegs, A, B, or C. What should this procedure do? First of all, it checks to see if n is bigger than 0. If n is actually 0, it doesn't do anything. It only does steps when n is bigger than 0. Okay, so 0 is the base case, and if it ever hits 0, it just ends. It just returns without anything, doing anything. But if n is bigger than 0, it does something. What's the first step that it does? Takes these 3 and moves them to the peg that I called using. So TOH, n minus 1, from, same from peg, but now the to peg becomes what I called before the using peg, and what I called before the using peg now becomes the to peg. Okay, let me stop. Other questions? Teresa?
You had 64 donuts to start with. You'd be moving 63.
Right. I'd probably get somebody else to move the 63, but yeah, somebody'd have to move them. All right, now I've done these 3, and I moved them here. The next step is to move this guy from to 2. So I'm going to display this. Display move disk from the from peg to peg. So if I put little quotes around something, I mean I just wanted to print those words. Move the disk from here to here, peg. All right? So I'm going to move it from whatever this is equal to whatever this is equal to. A to B.
You can't do that with a call to
No. Well, if I did,
This is just so you can see what's going on. Otherwise, the algorithm will run and.
well, if I did this with a, let's try to answer this question without getting too far off track. If I did TOH here with 1 from 2 using, the first thing it would do is it would get to here, see that it's bigger than 0, do this would be empty, and then it would do this, TOH1 again, and it would just be in an infinite loop. If I call TOH here, it would be an infinite loop. There would be no place, there would be no way for me to actually see this disk move.
Plus, this is within TOH anyways. The display.
That's true. At some point, you have to say move something from somewhere to somewhere. But if you're still not quite sure, you should go ahead and actually write that up in Scheme and see what happens. You're going to hit return, and it'll just go forever. And we could write it out and check that ourselves, but maybe it's not best to do it right now. What's that?
Use Donna's program to check my program.
Right. Then we would know not to have to run your program. All right. The last step, this is already here. We're going to take these 3 and move them on top of here. So TOH, how many disks? N minus 1. And where are we moving them from? We're moving them from the using to the 2, to the original 2. And we're going to be using the original from peg. Close the brackets. So Sam asked me, why is this pseudocode? It's pseudocode because if I type this into any compiler in the world except one that I wrote myself, it wouldn't compile. Right? I mean, in C, you'd need little semicolons here, and you need some declarations of variables, and Scheme, you need more parentheses. It's just, you get the idea. It's a pseudocode, and you could turn this into Scheme if you wanted to, or into any language for that matter that has recursion built in. Are there questions about this?
So is all this in the affirmative case for the if? All that we've heard
Yeah,
so far?
from here to here.
Okay.
And otherwise don't do anything. All right, so let's actually run through this algorithm, at least for 3 disks. How do I move these 2 disks from here to here? I call Towers of Hanoi again, and I move the top disk over to here, this disk over to here, that's the middle step, and this one back on top, that's the 3rd recursive call of the 1st recursive call. Now I'm finally up to the 2nd step of my original recursive call. This goes here. And now I make a 2nd recursive call for Towers of Hanoi 2, which says move this here, move this here, and move this here. And if I was doing it with 4, things would be a little different. Now my goal is to move these 3 to here. How do I move these 3 to here? I've got to move these 2 to here. How do I move these 2 to here? I got to move the first one to here, this one here, these 2 are here. Now the middle guy can come here where I want it to be. Now these 2 have to move back on here. Now I can finally do my middle move. Take this red and put it here. Now I got to take all these 3 and put them back on this side. In order to do that, I got to get these 2 over to here. So how do I do that? Here, here, here. This one goes back here, and then here, here, here. Which one's black? All right. So let's roll this out of the way. You should play with that toy for a little while. Make sure you can do that yourself. I mean, once you get it for 4, I think you can pretty much get it. You won't lose track of where you are. But 64, I don't think you need to do. That'll take you too many years. Let's analyze how long this algorithm takes, and then see where we head from there. T of n is how long this algorithm takes. What does it consist of? It consists of 3 steps. The first step is a recursive call on n minus 1. So that's, how much time does that take? Tn minus 1. I don't know how much time it takes, but I know it's called Tn minus 1. And this takes one step, and then I got another Tn minus 1. So I get 2 Tn minus 1s plus 1. And when n is equal to 0, how many steps does this take? 0. That's my recurrence equation for the time complexity of towers of Hanoi. What I need to do now is just figure out what this is. So a lot of you know that this is going to end up being 2 to the n minus 1. We're going to calculate this exactly.
But just looking at it, you realize it's the order 2 to the n.
Some people do. Yeah. Why would you? Because you're doubling the time complexity every time you take away 1. So if you double something every time you take away 1, then by the time you get down to 0, you've doubled it n times, and that's 2 to the n. So it's true, and you should develop intuition like that. It's worth having, instead of having everything being a mystery until you get to the end. You should know what you're kind of expecting here. In general, in a recurrence equation, if this number is going down by 1 and there's some multiplicative factor here, your solution is going to be exponential. If this gets cut in half or gets cut down by some multiplicative factor, half or a third or a fourth, then well, if there's nothing here, then it's going to be logarithmic. But what if it's 2 Tn over 2? There's all sorts of variations on this. Some of these recurrence equations come up so frequently in algorithms that there's kind of a master theorem that lets you deal with many of them all at once. But that master theorem comes precisely, the proof of it comes from doing these substitutions and getting general summations and analyzing what the order of complexity is of those summations. And we'll get to that in a couple of days. There are other recurrence equations that are more mathematical that don't come up as often in algorithms, but we're going to study how to solve some of those basic ones as well. But first, let's do this just with the repeated substitution. Teresa?
Could you do it again, time 2n minus 1 plus 1 to that code?
Yes. The first step is the same code again, but just on a size of disks that's 1 less. So if we say this takes Tn time, then this is going to take Tn minus 1 time, because it's the same problem.
Okay.
So that's Tn minus 1. And this takes 1 step. That's this 1. And this takes the display.
Okay.
Because all you're doing is printing it out. You do one thing.
Why do we, I'm just sort of surprised that's in the code. That almost seems like an extraneous step or something.
Well, you're moving the disk from
Yeah, well, I mean, if you don't have this in the code, then you never actually see what's happening. This is equivalent to me picking up a disk and moving it over here. This is the only place we ever say what happens. This is the only place we ever report what's going on.
Sort of like a placeholder, so we know
Well, in a
we've
sense,
done something.
if you look at the program as not just telling you how to do it, but actually doing it, then that's the only place where disks actually get moved.
This is the only place where disks actually get moved, right?
Move disk or something, which could be another.
All right.
Right. You could make this a procedure called move disk. This is the only place we actually say, let's move a disk.
Okay.
These are all recursive calls, which eventually we'll get to calling this one line.
Okay.
And now this thing down here is another recursive call. It's actually a procedure that runs again, and the parameter is n minus 1, so again it takes Tn minus 1 time. So that's where you get 2 Tn minus 1. Okay?
You're counting the display as 1?
Yeah.
Aren't you going to also count the bottom disk that you moved over as 1?
That is the bottom disk.
Maybe if you just change that to move or something, like that procedure.
Yeah.
If you programmed a robot, that would be the.
display is the
If you programmed a robot, that would be the command that to make the robot.
The result of this is going to be a list of instructions for how to do this.
Right. The result is a list of instructions. Here, I'll call it robot move. Right. This does the recursion for the first top n minus 1. This moves the bottom one. This does the recursion for the top n minus 1 again. So this does move the bottom one. And in fact, it moves the bottom one on every single pile. Even piles of 1, this moves the bottom one, which is that particular disk. That's why we can't call Towers of Hanoi again for a disk of 1, because then we don't end up moving any disk. Okay. Other questions? Let's run through this step by step. This is going to come up with a result which gives us a summation instead of just one number in the repeated substitution. So let's go through it. Again, as before, we start with this, and we want to get rid of this. So we write down Tn minus 1 equals 2 Tn minus 2 plus 1. And we're going to take our value for Tn minus 1 and put it back in here. And this time we'll be a little more careful because you can make a mistake if you're not careful. 2 times 2 Tn minus 2 plus 1 plus 1. I took this, I replaced it into Tn minus 1. And I did it slowly because some people, not Sam, will not see exactly what this works out to be in advance. So look at it slowly. Now see what it turns out to be. 2 squared Tn minus 2 plus, right, plus 2 plus 1. I'm going to write it out, leaving the summation there. Don't simplify it, because if you simplify it, you will lose the pattern. Try to leave the pattern. Let's do this a whole bunch more times. I'm going to erase the algorithm. Everybody have this? If you don't have it, you can find it in every single programming book ever written in the last 30 years. Just look up Towers of Hanoi in the back. You can look at it in Java and C++ and Scheme and Visual Basic and I don't know. Anything you ever wanted. What's the next step if I did it one more time? Can you see a pattern? What's happening? This bumps up by 1, right? So you'll get 2 cubed T n minus 3. And look at this. What would happen here in the next time? The next time through, this stuff gets multiplied by 2. So you get 2, 4. And then 1 gets added at the end. So you get 4 plus 2 plus 1. So now what happens when I do it a lot more times? When I do it r times. After r times. This number becomes 2 to the r. This becomes Tn minus r. And this, what's the biggest term here? It's not 2 to the r, right? 2 to the r would be 8, the biggest term. The biggest term is 1 less. So you get 2 to the r minus 1 plus 2 to the r minus 2 plus dot, 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 all the way down to 4, 2, 1. That's the typical kind of thing you get when you do recurrence substitutions. You don't just get a nice sum, you get sometimes these dot, dot, dot things, and you got to figure out how to add them together. And now we're going to talk a little bit about how to do this, what geometric series are, variations of geometric series, and things that come up frequently in recurrence equations, and explain to you how to solve them. I'm going to teach you one trick in doing this, a trick that will work in the vast majority of situations that come up, and you don't have to memorize anything. And I really urge you not to memorize anything, because you're more likely to just waste the brain cell memorizing, be too busy to think about what's going on, and then apply it wrong. If you just think about the idea here, you'll never go wrong in solving one of these geometric sums. And I'll show you what I mean. Right. We need to figure out a way to get rid of this capital T. So we're left with just the sum, and then we'll solve that sum. So how do we get rid of this capital T here? Here it's straightforward. What should the r be? R needs to be n because we know T0 equals 0. So if r equals n, let r equal n. We're going to get Tn equals 2 to the n times 0 plus, I'm going to reverse this now, 1 plus 2 plus 4 all the way up to 2 to the r minus 1. That's 0. 2 to the n minus 1, thanks. So here's our sum for how many steps Towers of Hanoi takes. We want to put this in a closed form, in an easier way to understand and perhaps calculate. And we're going to do that right now. Are there questions so far? John, okay?
No, I missed that last step.
This step comes from here. We're looking at this general formula that we got after doing this r times. And we want to make sure that this capital T disappears. So how many times should we do it? We should do it as many times as it takes this to turn into a 0. This turns into a 0 when r becomes n. Then you get Tn minus n. So every place you see an r, you put an n. 1, 2, 4, 8, 2 to the n minus 2, all the way up to 2 to the n minus 1. That's where this thing comes from. And when this becomes 0, T sub 0, that doesn't take any steps. That becomes 0. So we get 0 times 2 to the n, which just crosses out. Okay? Yeah.
What's
Teresa?
the logic behind saying I want this to disappear?
Because we can't get an answer when the t's on the right side.
Nothing more than that?
No, I mean, if somebody said, how many steps does it take? Here, there's 36 discs on the thing. How many steps does it take? How are you going to tell them an answer?
Okay, it's strictly to eliminate a term that we can't sort of otherwise deal with.
Right. Right. We want to be able to answer the question, how many steps does this take for a particular n? And if this is here, it depends on how many steps it takes for some other example. So if we really want to give them an answer, we want to basically unwind the recursion until it's all gone down to the base case and there's no more recursive calls. And this keeps track of what happens during that sequence of recursive calls.
Do we know what that term represents? Like why it's there? What part of the problem?
Yeah, it represents the subsequent recursive calls that get done later. And sooner or later, all those recursive calls will end. And this keeps track of how much work goes on until they end.
Okay.
So if you do that, yeah.
Getting rid of it, aren't we sort of counting the recursive calls?
Yeah, you are. You're counting the recursive calls and how much work gets done by each one of them. Because each recursive call, besides generating new recursive calls, does some work as well. It does that display, and then it has two other recursive calls. That's where these doublings started showing up. So yeah, we are doing that. All right, other questions? All right, so here we're up to here. And now I want to tell you in general, how do you get rid of sums like this? And there's a trick that's going to work for this sum, and then I'll do a more complicated sum after we solve this one. But here's the trick of how to solve sums like this. You just give it a name, call it x. Oh, and you're all done. No. Give it a name and it's happy. Give it a name, and our idea is we'd like to get rid of the dot, dot, dots. So here is something that happens in geometric series. What's a geometric series, first of all? A geometric series is a series that each successive term is multiplied by a particular number. So 1, 2, 4, 8. What's the particular number that it's being multiplied by? By 2 each time. It's going up by a particular factor. An arithmetic series doesn't get multiplied each subsequent factor. It gets added. So like 1 plus 2 plus 3 plus 4, that's an arithmetic series. 1 plus 3 plus 5 plus 7, that's an arithmetic series. We talked about those already, a lot of them. Now you're talking about geometric series. Euclid knew how to sum a geometric series 2,000 years ago, so we should be able to do it now. Yeah? No? Let's go. All right, how does this work? Here's the trick. If you multiply the geometric series by that multiplicative factor, it just takes the whole geometric series and kind of shifts it over to the right one. You did this in streams when you talked about it in scheme. 2 times 1 is 2. 2 times 2 is 4. 2 times 2 to the n minus 2 is 2 to the n minus 1. And 2 times 2 to the n minus 1 is 2 to the n. It just shifted everything over 1. And now if you subtract the top from the bottom, 2x minus x is x. And this minus this is, all these cancel out. They line up and they cancel out. Bye-bye. 2 to the n minus 1. And that's the answer. And you should remember in general, when you're adding up powers of things, and you add up every single power up to some length, then you just about get to the next power, missing it by 1. If you add up powers of things, 1, 2, 4, 8, all the way up to, say, 2 to the 3rd, or 2 to the 8th, then if you add all those things up, it's just 2 to the 9th minus 1. You're almost there. Okay? That should remind you of something. Does it remind anybody of anything?
Binary numbers?
That's not what I'm thinking of. I'm thinking of integration. This is like a sum of things, right? If you're adding up the sum of things all the way up to 2 to the I, it doesn't matter. All right, so here's how you do a geometric series. If this multiplicative factor was a 3, then you'd be multiplying by 3. If the multiplicative factor was a half, then you'd be multiplying by a half. All right, so another example, Zeno's paradox. I did this before with you a couple months ago, but we'll do Zeno's cake paradox today. You're sitting at a dinner. Somebody has a big piece of cake. They cut it in half, they give you a slice. You're a very polite person, so you look around the table and you see somebody else doesn't have a slice, and you say, oh, would you like to share my slice? So you cut your slice in half and you give them a slice. And then you keep doing this and you keep doing this, and somebody says, whoa, well, we can just feed like a multitude. It's a religious parable, right? We just keep slicing the cake in half. Another slice of cake, Zeno? Well, what happens if you keep slicing the cake in half? What happens when you keep slicing the cake in half is that you actually get just one piece of cake when you're all done. X is the piece of cake. The multiplicative factor here is what? 1/2. So multiply this by 1/2, and you get 1/4 plus 1/8. And the nice thing about infinity is that you don't even have this extra term at the end that you have to worry about, because everything just matches up at the end. It goes forever. So when you subtract x minus 1/2 an x, you get 1/2 an x, and what does that equal? Equals 1/2. So x equals 1. Just one piece of cake. All right, there's an example. Let me show you an example of a fancier geometric series that isn't really a geometric series. It just looks a little like one, and show you how to do that, and show you how to do a gazillion things like it using the same trick. Just remember this trick. You never have to memorize any formulas. Questions? Questions? Okay. And let's do this underneath it. This is a geometric series. This isn't. If there were just ones up here, this would be a geometric series, but there's not. There's this increasing arithmetic series up kind of up on top in the numerators, and just the power geometric series in the bottom. But put together, it's not any series that you're used to. And here we normally get a problem. Let's review how to do it here in the easy case. Who can do this at their seat and tell me what you get for x?
1/9.
I guess the right answer would be one of you to yell out very quickly, Sam. I said, who could? I didn't actually ask for the sum. It is 1/9. And it also equals 0.111111, forever. Right? 0.1, 0.01, 0.001. So that's 1/9. And you can do it just the same way we did. I won't do it again, but the multiplicative factor is 1/10. You divide by 1/10, you subtract. You do it at your seat. Make sure you can do it. When you get to something like this, your gut instinct is, well, I have no idea how to do it, so I'll go ask Shai or the TA or something. Or you can say, well, I have no idea how to do it, but I have one tool in my bag of tricks that worked on something similar, so I'll try to fit it on this. And if I break the tool, then I'll give up. Or if I get something that looks terrible, I'll give up. But if I get something that's good, then I'll know that tool is kind of a little more versatile than I originally thought.
If your only tool is a hammer, the whole world looks like nails.
There you go. Right. Right. And if the whole world looks like nails, then you need a vacation. All right, let's do this. Same trick as before. 1/10 x. Not because we know it'll work, but because we're just going to try it and see if it works. What happens when you multiply this by 1/10? This piece becomes 1/10 squared, and this piece becomes 2/10 cubed, and this piece becomes 3/10 to the 4th, etc. And now let's do the same trick we did before. We'll subtract this from this. X minus 1/10 of x is 9/10 of x. Now look what happens. 1/10 minus 0 is 1/10. 2/10 squared minus 1/10 squared is 1/10 squared. What happens here? Good, 1/10 cubed, and the whole way down. Since we shifted it over, nothing canceled like before, but things got simpler than they were. We used to have an arithmetic sequence here. After we do the subtraction, this arithmetic sequence has simplified down to a constant sequence of 1s. What does that equal? Who knows what that equals? 9/10 x equals a ninth. So x equals 10 over 81. This equals 10 over 81. Okay. That trick works a lot. It's an easy trick to remember. It works for geometric series. You can derive a general formula for your geometric series with this trick. It works for series where the top goes up by an arithmetic amount. What if the top went up by a squares? What if I had 1, 4, 9, 16 up on top? What do you think would happen? The first time you do it, it reduces to a linear sequence. The next time you do it, it reduces to a constant sequence. The next time you do it, you get an answer. What does that remind you of? Reminds you of derivatives of polynomials. Cubes turn into squares. Squares turn into linear terms. Linear terms turn into constants. Constants turn into simplicity. All right? And it's not an accident. What you're really doing here is virtually taking a derivative. You're really putting in a particular value here for x. You put in another value for x here. You subtract the two. You divide by the difference between them. It really is a derivative if you think about it. And sometimes it's called a finite difference. It's a discrete version of a derivative. So it's not an accident, and it's not just some hocus pocus weird, isn't that cool? There's no magic about it. If you actually analyze it, you'll see why. It really is like a derivative. It's taking the differences between successive terms in a sequence, and that's what derivatives really are. The rate of change of a sequence. So squares change at the rate of linear time. Linear sequences change at a constant rate. All right. So now you can solve any kind of series like this where the top is any kind of simple polynomial and the bottom is just exponents. You just have to use this trick over and over and over again. All right, questions about this? All right, so that's Towers of Hanoi example. This is geometric series and variations of them. Now I'm ready to start on a problem which is a lot harder than Towers of Hanoi. But before I do it, I want to give you the bird's eye view of Towers of Hanoi. I want to take you out of the jungle of the computation and out of the summations here and let you see a picture. For people who are particularly visual minded, this will be like an epiphany for Towers of Hanoi. And even those of you who feel you completely understand Towers of Hanoi, I think this will still be somewhat of an epiphany. It makes you feel like, oh, now I can see what's going on completely. All right, so here's how I'm going to represent the Towers of Hanoi. I got 3 pegs. We'll number these pegs 1, 2, and 3. And if I place a donut on a particular peg, then I'll write 1 if that donut's on peg 1, and 2 if the donut's on peg 2, and 3 if the donut's on peg 3. So here's an example of the Towers of Hanoi problem with 1 donut. There are 3 possible configurations in this problem. The donut's here on peg 1, the donut's here on peg 2, or the donut's here on peg 3. Everyone agree? Let's make a picture, a graph picture. Every one of these configurations, every one of these rows now has a node in my picture, a vertex in my picture. I'm going to label this one 1, I'll label this one 2, and I'll label this one 3. I made a triangle here for a very particular reason. You can make a move from 1 to 2. You can pick this disk up and move it from here to here. If you can do that, then I connect 2 vertices in my picture. 2 vertices are connected. 2 configurations in the game are connected if you can move in one step from one to the other. I can move from 2 to 3, and I can move from 3 to 1. I can move from any one to any of the others. This is such a simple case, it doesn't seem like it's giving you much at all. But the very next case for 2 disks is going to give you a lot more. And will give you a real nice sense. And I'm going to go up to 3 today, and then I'm going to run out of Blackboard. But you'll see a lot when we get to 3. So let's write down all the possible situations for having 2 donuts on our 3 pegs. See how many there are. See if we can make a picture, and see if the picture gives us any perspective. Here's 1. There's a lot of these, right? How many are there going to be all together? Anybody know? How many 2-disk configurations? Let's write them out.
9.
8, 9? Let's try to write them out.
First of all, the ones with the...
Why don't I leave the bottom one here and just move this one over? So I've got 3 with the bottom one on peg 1. Agreed? I'm going to get another 3 with the bottom one in the middle. And I'm getting another 3 with the bottom one at the end. 3, 3, 3, that makes 9. Right, when we get to counting in another week, this will be an easy problem. You'll glance at it, you'll think about it, and you'll blurt out 9, just like Sam did. Okay? But right now, it maybe take a little bit of thinking, and I don't want to get into the counting part of it yet. I want you to just realize that there's 9, and I want you to realize the following thing. That we started with 3, now we're up to 9. And we're going to create this new graph the same way we created the old graph, but instead of flailing around and just making 9 vertices and connecting them where we might not see the pretty picture and unravel it well, I'm going to specifically make a very particular picture here to save you the horrible dead-end effort of discovering this pretty graph for yourself. So here's how it's going to look like when we're done graphing it. I'm going to relabel this with 1s on the right end. Which 3 configurations do these 3 nodes correspond to? What do you think? These 3 here. What do they mean? What do these numbers mean now? I put 2 numbers down because now every node represents a configuration, and every configuration has 2 donuts in it. So I need 2 numbers to represent what it looks like instead of 1 number. This number represents the bigger one. Bigger, smaller. That one represents the smaller disk. So this means that this configuration means that the bigger one and the smaller one are both on peg number 1. That's this guy. Okay? This means that the bigger one's on 1 but the smaller one's on 2. The bigger one's on 1 but the smaller one's on 3. Why does it have the same structure as the original? Because the bigger one is staying on the same peg. If the bigger one stays on the same peg, then it's just as if it wasn't there at all. Erase the big one. 1, 2, 3, the same configurations we had before. So it's the same triangle. By the same notion, if I move the bigger one to the middle, I'd also have a triangle of configurations as long as I keep the big one on the second square, I can move from 1, 2 to 2, 2 to 3, 2. Because the big one stays where it is. Think about this a lot. There's going to be a problem set on this that you're really going to have to understand how this works. So get the basics down before you have to really do the hard stuff.
I don't understand why you've labeled the vertices the way they have instead of having 1, 2 at the top. It doesn't matter.
Oh, why did I rotate these the way? It matters a lot. And I'm pretending like I did it randomly, and I did it very purposely like this. I'm sorry. It's like a date, and you're about to break up with somebody, and they go, "Is there some reason why you canceled our date for 3 weeks?" And I go, "No, that was just complete coincidence." No, I'm fooling you here. I'm making this seem like it's obvious, and it's not. What you really end up doing, Gary, and I'll tell you the secret now, it's that you put this up here, and when you add the 2 to the same picture to make another triangle, you rotate it once, so that the 2, 2 is over here in the corner. And you'll see why in a second. So we're going to do the same thing here. Let's put the big one on the third disk.
This is a graph of what now?
It's a graph. It's a good thing. It's a graph of how you move from one configuration in the Towers of Hanoi problem to another. This graph is going to be the 2-disk Towers of Hanoi problem. And if you want to watch a set of movements, it ends up being a path on this graph. Okay? I can go from here to here, right, by moving the top over here. What edge does that correspond to in my graph? Moving from here to here. No, sorry, moving from here to here. 1, 1 to 2, 1. Any movement in my graph corresponds to an actual change of the configuration in the Towers of Hanoi by one move. That's a good question. If you weren't sure of the answer to that question, that's a super question. That's really what we're doing. And I'm going to explain it more, but let me finish the picture for this graph so you can see all the edges. So let's put the big disk on the third one. If the big disk is on the third one, all these things start with 3 here. And the smaller disk can either be on the first, the second, or the third. And these connect just like they did before, because the big one's on the third one, and that doesn't affect anything about the top disk. The top disk can still move from 1 to 2, 2 to 3, and 3 to 1. The question is, how do we reconnect? Now that we've increased to another disk, and we've made 3 copies of what we had before, adding the bigger disk on the bottom first peg, adding the bigger disk on the bottom second peg, adding the bigger disk on the bottom third peg, how do these things connect to each other? Which configurations can move to which? The configurations between, the edges between these two correspond to when you're actually moving the bigger one. When can you move the bigger one? Let's do a possibility. We can move it from here, right? If this is the smaller one and this is the bigger one, we can do this move. This is the number that we write from right to left as 1, 3. This is the number we write from right to left as 2, 3. So between 1, 3 and 2, 3, there should be an edge. This edge corresponds to moving the bottom disk, to moving the bigger disk. See how the big disk changes and the small disk is different? Notice the small disk had better not be on either 1 or 2. Otherwise, you couldn't move the big disk. Right? The small disk is away on 3, and we can change the big disk from 1 to 2. Here, the small disk is away on 2, and we're changing the big disk from 1 to 3. Here, the small disk is away on 1, and we're changing the big disk from 2 to 3. That's the whole graph. A sequence of movements. When I sit there with that table and I move donuts around, every time I move a donut around, somebody, and this would be really cool if I actually wrote a little Java applet to do this, but I haven't done it yet. I could have somebody with a little robot move donuts around, and as they moved, you'd see a little red light moving from one place to another on this graph. So that somebody playing with the picture of the game would be able to see directly what path it corresponded to on my graph. That's what this graph represents. Every node represents a position in the game. Every edge represents a one-step movement from one position to another. Questions?
The peg numbers are constant in this, right? In each triangle, peg 1 is the top, peg 2 is the lower right, and peg 3 is the lower left.
Yes. 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 I'm going to get into that in a second. Yeah, John?
I missed why we're actually writing those. If you compare the way the numbers are written on the triangle to the positions of the rings on the pegs.
Okay, let me make that one-to-one correspondence completely clear.
I just don't understand why you write it that way round. I mean, for instance, the bottom one there you call 2, 3, but you write it 3, 2 from left to right on the
So you're saying he's writing it from right to left.
I'm just, the bigger ones are on the right end, that's all I mean. You have to decide what direction you want to go here, and I decide I go from left to right goes from smaller to bigger, right to left goes from bigger to smaller. But this number represents what peg the biggest disk is on, and this represents what peg the smaller ones. Okay, you got it. Oh yeah, no, I just picked it. In fact, you can see a good picture of these things in a book that I brought in today by Ian Stewart. That's the guy who gave the talk about the Minesweeper game. He writes lots of popular math books, and in one book that I brought in, he's got a chapter on Towers of Hanoi, and he's got a picture of this graph, and I think actually he might actually have the opposite convention. So looking at his book might confuse you, but it is arbitrary. All right. Now that everybody's got this, let's look at the solution to Towers of Hanoi. I want to move this to here, right? Let's do the solution. It's a 2-disk. It's not going to kill us, right? What's the next step?
Going down one side.
I mean right here on this picture. Small disk here. Big disk here. And finally, we're all done. Now let's follow this on the graph. This is the position that we call, here, peg 1, peg 2, peg 3. This is position 1, 1. What's this position?
2, 1.
Where's the bigger one? The bigger one is on 1. The smaller one's on 2. Okay? We go from here to here. This is actually moving that larger one, right? The bottom one. Moving the bottom one means moving the biggest one, the rightmost one. Changing the rightmost one is done here. And finally, that's the last one, being 3, 3. If somebody showed you this graph and said, you start at a corner, how do you get to another corner? Would you sit there and scratch your head for 5 minutes trying to figure it out? Would you say, oh, this is a deep problem. I don't really see how to do it. Teach me about recursion so I can understand the idea. You wouldn't. You'd say, let me give it to my 2-year-old, right? Boom. It's so obvious what the fastest path is to get from one corner to another. You just have to stare at it. The graph lets you build in on every natural human advantage you have. All right? You don't have to build a robot to notice that that's the fastest path. A robot might not be good at it, but you can see it in a flash. And that's why graphs are powerful. If I asked you to move it to the second peg, you can also see it's just a straight line. Any detour is going to take you longer. You'll also notice this. What if I asked you, from any point in Towers of Hanoi except the starting and finishing points, how many choices do you have? 3, right? The starting points you have 2, but all the others you have 3.
Wait, what are... Now I'm trying to picture that. You can move the top one over here, or you can move the top one over here, or...
It actually isn't so easy to figure out the possible cases, but if you stare at the graph, it's automatic. There's 3 cases that you can move to no matter what. Sometimes it's twice for the top one, sometimes it's none for the top one. But there's always 3, except when they're all in one
because the small
peg.
one can move to 2, and the big one can move to 1.
Right, right. But this just gets it all at once. Boom. 3 choices.
There's never none for the top one.
Yeah.
No, I meant the bottom one. Sorry. The bottom one sometimes is none. For the top one can always move. Absolutely. Right. Rob's asking a great question, right? Are we just getting lucky for the second stage, or is this just going to like build up like a snowflake?
Does it go multi-dimensional, and does it look like a, what is it, Karloff's triangle, or is it kind of like...
Sierpinski's triangle? It looks just like Sierpinski's triangle. I'm not kidding. It really does. Now we can spend an hour talking about Sierpinski's triangle. I once had a student that did a research project that had nothing to do with this. It had something to do with some matrix manipulation. And in the middle there, he started printing out zeros and ones. And then he wrote some comment in something that I was supposed to edit. And he goes, this is just like Sierpinski's triangle. And at that point, I'd never heard of Sierpinski's triangle. So I said, well, what is Sierpinski's triangle? And then I found out that he had no idea either, that he just kind of saw a picture somewhere. So I ended up having to look it up and figure out what it is. And it's got connections to a lot of things. And it has a connection to this. But let's not go there. Let's look at the case for 3. Just as the case for 2 is built out of 3 cases for 1, with single edges connecting the bottom moves, the case for 3 is built out of 3 copies of the case for 2, with bottom edges connecting those 3 copies. Basically, if you have 2 disks, it moves around like this. This is the structure for 2 disks. If I add a big disk on the bottom, the structure remains. I just have to figure out how those 3 different copies, where the bottom one's on peg 1, and the bottom one's on peg 2, and the bottom one's on peg 3, how those 3 copies of 2-disk problem connect together. And what's neat is that they connect together in a way that should remind you of the recursion. Here's the recursive part. Here's the display. Here's the recursive part. Here's the recursive part. Here's the display. Here's the recursive part. The display part is the part that moves the bottom one. From here to here is the recursive part. Now let me show you in a bigger picture so the recursive part is more than just one move, because that's what it's typically going to be. So here we're going to have to really draw carefully. We're going to need 3 copies of that. There's 1. There's 2. Bleh. Okay, there's my 3 copies. Let's label them to make sure we can all do this. The top copy is going to be this one. Okay, it's going to be 1, 1.
Well, it's 1, 1, 1.
I'll add the I'll add the third number in a second. 2. I just want to show you that it's this copy, the 2-disc one, and then when you're all ready to believe that, I'll throw the bigger disc on the bottom of the first peg, because the top 2 still move in this relation. So 2, 1, 3, 1. Help me out. 2, 3, 3, 2.
2, 3, 3, 1, 3, 1, 2.
Okay. And just like I said, this is going to represent the case where we take the new disc and we throw it on peg 1, which means it's on the bottom of peg 1. The other 2 discs move in this notion just like they did before, but at the right end where we put the biggest one, it sits on peg 1. 1, 1, 1, 1, 1, 1, 1, 1, 1. All right. Now, in order to label this one, we have to figure out what this guy is. Remember, this represents a movement of the biggest disk. So where do the small disks have to be here if the biggest disk is moving?
Away on the same place.
They have to stay where they are.
2, 3.
I'll go for 3. Good. It's the only possibility.
I'm sorry, what do you mean the small disks need to stay where they are? So the big disk is on, okay, the big disk is on 1.
The big disk is on 1.
Let's move to 3.
Any movements that aren't the big disk are taken care of in these pictures that I've already drawn. The only movements that aren't taken care of are the movements between configurations where the big disk moves.
Okay.
Because the big disk stays the same in all these configurations. That's why it's the same structure as before.
Okay.
So this 3 is going to stay 3 here for all these values. Let's label them. Notice, you have to take this and watch it. Rotate it up. So what do we get? 2, 2, 3. I wrote it down so I can do this without messing up. But I like you to yell it out so you can think with me. 3, 2, 3. Everybody see what I'm doing? 2, 2, 3, 3, 2, 3. Going up this way is going down this way. Okay? What's this one? 3, 1, 3. Good. And this one? 1, 3, 3, 3, 3, 3, 2, 3, 3, 2, 1, 3, and 1, 1, 3.
It's important the 3, 3, 3 be in the corner.
Right.
2, 2, 2 is also going to be in the corner.
Right. I guess here I have a choice as to which way to label these, but if I just follow the orientation and stay consistent and make sure I have 3, 3, 3 in the corner, everything works out okay. Here I'm going to have 2, 2, 2 in the corner. So let's label all these. Here I want to move this one from 1, 1, 3 to 1, 1, 2. And this one, 3, 3, 1 to 3, 3, 2. And now I can fill in the rest. 1, 3, 2, 2, 3, 2, 1, 2, 2, and 2, 1, 2, 3, 2, 2, and 3, 1, 2. That's Chicago. That's New York City.
Well,
That's Connecticut.
if you get to the 7 case, we'll have Massachusetts.
Whew. Now they have area codes. I used to give a problem in finite state machines, to come up with a finite state machine that does area codes. Because area codes used to be normal, right? They used to have like a digit, a 0 or a 1, and then another digit. But now you can have any area code in the whole world. So I had to, when you get old enough, you got to change your problem sets because the examples you use change. Like imagine you're using a phone. How long would it take you? How many What if you're dialing the number 1, 2, 3, 4, 5, 6, 7, 8, 9? How many inches does your finger move? Right? That's a great problem for triangle numbers. Okay, but only before 1971 or something, right? If you do the problem now, how long does it take? I don't get it. Do you mean?
It's gone linear.
Yeah, it's gone linear, right? Let's connect these. Ooh, this is tough. 1, 2, 3. So the answer to Rob's question is yes, yes, and yes. It's exactly the same structure. To go to 4, you'd have 3 of these and connect them again with 3 new edges. There are so many things you can learn from this picture. I just showed you a couple. I showed you how you can see the obvious shortest path and actually figure out what the moves are. I showed you how this represents the recursion. From here to here is the recursive call. That's the display. From here to here is the recursive call. Here's a sub-recursive call. The recursive call here has 3 parts. Recursive call, display. Recursive call, display. It all just shows up like a picture. It's a great picture. I love this picture.
And the number of steps to get from one cone to another is 2 to the n minus 1.
Right.
So just to clarify the way that it's rotated, is it kind of like if we were to take the corner that connects and swing it around so that it drops from that?
Right, exactly. Okay. And then swing this around the other way and then connect them all up.
Yeah, just as if we put a
right. Again, right. In fact, somebody who's really good at doing little Java applets and has a good visual sense, I'm sure can make a beautiful little video of this, just showing how these things, rotate around and connect together, and then the next one grows. It would just grow in front of your eyes. Just the kind of thing I wish I could do well, but usually I don't do it so well. You can see how ugly my picture is here. But the idea here is really beautiful, regardless of the picture. This is black, this is white, this is black, this is white. If I alternate the colors, black and white, on these disks, and if I add the constraint, don't ever put black on black or white on white. Make sure that they stay alternating. If I add that constraint to the normal Towers of Hanoi constraint, then the choice at every point is no longer 3 choices. It's only 2 choices. And going from one state to another state is simply a matter of making sure you don't go backwards. The problem solves itself. You can write an iterative algorithm to solve it. Just say move, don't make the last move you made, and follow the rules. Right? No, same thing, different size disks, same as before. Let's do an example.
It would still be at least, it would be more than in.
It's going to be the same solution.
Really?
Yeah, it's the exact same thing.
Yeah.
Watch. We'll do it with 3. You know what? This is so easy. Well.
So yellow and red can't go on green and orange.
Yellow and red can't go on green and orange. Jeez. I'm going to mess up. Let's do it with 3. Green can't go on orange. Okay? I want to move it from here to, say, here. All right? Green can't go on orange. 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 You don't have to do anything. There's a little detail to this. The first choice you make actually could be wrong. And if you make the first choice wrong and you go in that direction, you'll end up going around this way instead of that way. That's the only thing you can do wrong. At the corner, if you make the wrong choice, because at the corner you have a choice, right? You can make the wrong choice there and go around this way instead of this way.
If you care which peg it goes on.
Right. But if you don't care which peg it goes onto, this is completely foolproof. Just follow the rule. No bigger ones on small ones. No black on black. No white on white. All right. So when you first tell people this, and they know the recursive solution, you say, well, try to figure out why the recursive solution is the same as this. And it's not easy to see why these two are the same. But you have a fighting chance with this graph. Right? And one of the problems on the p-set is to try to explain why those two are the same. Why it's true that if you go from here to here in the recursive solution, which is the same as saying if you go from here to here on this graph, why do you never ever put a disk on an even spot on top of a disk on an even spot, and a disk on an odd spot on top of a disk on an odd spot? Why do you keep that black-white alternation steady? And the way to prove it as you might guess, is by induction, because you assume you never do it for these smaller triangles, and all you really have to concentrate on are these connecting pieces. With all this hint in place, this is not an easy problem. I gave you a lot of hints in the problem set to help you try to do it, but if you can really do this problem, then you've used mathematical induction for a purpose which is not just an illustration of the technique, but which you really, really have a hard time proving this straight up. And with induction you have a chance, and with this graph you have a chance. This graph is inductively defined, and the proof is built up out of pieces of this graph. There's a lot of other things you can get from this graph, but I think I've kind of shot my load here trying to build up how cool graphs are. But here's a great example of it. All right, are there questions about this? All right, here's what we're doing next time. Next time I'm switching over to that other puzzle, to that 6 rings puzzle or 7 rings puzzle. That puzzle is also a puzzle that can be solved with recursion. I want to give you, since you have a day now to go back and look at it if you haven't solved it yet, I want to give you some hints that will give you a sense of what that puzzle is like before I will show you tomorrow what's going to happen. Tomorrow we're going to go through and analyze that puzzle just like we did Towers of Hanoi. I'm going to connect it to a bunch of surprising things. You should know that in the store you can buy puzzles that are equivalent to that puzzle I gave you. There's a little puzzle called Spin Out that you can buy in any toy store with a little track and little things that turn right and left, and you have to pull out the track. That's equivalent to the 6 ring problem. There's a couple other problems equivalent to it. Here's something you should know about this puzzle, and it's a little frustrating to know, especially if you've been working on the puzzle for 8 hours and haven't discovered this yourself. You see how in the Towers of Hanoi you have a choice? You go down here and now you've got 2 other choices where to continue, backwards, and 2 new forward choices. In this 6 rings puzzle, it's not that complicated. If you go forward to a particular position in the 6 rings puzzle, do you know how many choices you have? You can go backward or you can go forward. That's it. So if I showed you the graph of the 6 ring puzzle, what would it look like? Where'd my eraser go? Yeah! Whoa! Out of control. Hold on. Uh-oh. Put it in my pocket. The graph of the 6 ring puzzle looks like this. If these are 6 rings all on, and these are 6 rings all off, say I made a vertex for each picture, you know, when a ring is on and when a ring is off. And this is node 1, this is node 2, dot, 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 dot. It's one line. It's a long line. It's completely trivial from the point of view of this graph to solve this puzzle. Either you're going forward or you're going backward. All you got to make sure is that you don't turn around. If I put it out like this and I said go from here to here, a 9-month-old can do it. If we put peanut butter here, and a 9-month-old can do it. A rat can do it. The thing about that puzzle is it's so convoluted in all the rings clanking and clinking and trying to squeeze this up is you don't even notice when you've been to a position before. You think you're making progress? It would be the funniest thing to watch somebody fiddle with this the first hour and watch a little picture on a screen of what positions they were up to. This is what they would end up doing. I'm getting somewhere now. Oh yeah, oh yeah. It's comical. I mean, I did it myself. It's comical. It took me 3 hours before I realized this. And then I smacked myself in the head and said, oh, there's only one direction to go here. But you have to come up with an idea of taking these big, ugly mechanical things and associating a vertex with each one and noticing what position you're in when you get a big mess of metal in your fingers. And when you get to that point, then you can tell whether you're going forward and backward. Now, that's just the beginning of this puzzle. It turns out that the way we're going to identify positions is going to be with binary numbers. So if a ring is on, it'll be a 1 in that position. And if a ring is off, it'll be a 0 in that position. So we'll have binary numbers of length 6. There's 64 of those. So there's 64 positions in this game. We're going to go from one to another. We're also going to calculate how many steps it takes us to go from one to another. The sequence of binary numbers that start showing up turns out to be the same as a completely separate sequence that comes up in computer science called gray codes. And gray codes were originally created not for this purpose at all, but for the purpose of when you have a little spinner around and you want to see what the spin was. If you're on the line, you don't want the binary sensors to be too far off, more than one or another. I'll show you where gray codes come from. But they don't come from here at all. They don't come from this puzzle. Nevertheless, this puzzle generates gray codes. All right. And none of this has to do with recursion yet. The most beautiful part of this puzzle is that there's a recursive solution to this puzzle that happens to generate gray codes on its way down. And in the recursive solution to this puzzle, calculating the recurrence equation gives you something like this. Remember, Towers of Hanoi was 2tn minus 1 plus 1. So now we got 2tn minus 2 plus tn minus 1 plus 1. If it was just 2tn minus 2, we could probably do what we did before. That same substitution idea. We're going to do substitution on this tomorrow for about 5 minutes until we get sick to our stomach of the ugly sun that starts showing up. You get a horrible, ugly sun when this shows up. And we're going to have to give up on that naive substitution idea. And we're going to give up on it big time. And tomorrow, for the one time in the class, I am actually going to not just show you the end of it. We're going to go down a planned dead-end alley trying this and back up, and we're going to pretend we're mathematicians instead of just some mathematician telling you about stuff. We're going to try to solve it by just making a table. We're going to pretend we're clueless. And we're going to make a table. And everybody in the class...
Study hard tonight.
That's right, method acting. We're going to pretend we're clueless. We're going to make a table of how many steps this takes. We're going to actually build it up from the base case up. And we're going to look for patterns in that table, just like somebody would who didn't know the answer to this at the beginning. And we're going to notice patterns in this table. They're not going to be that hard to notice. And we're going to say, oh, gee, I wondered why I didn't see it looking at this. Well, because you don't do this all day long, your whole life, and you don't notice patterns when you see it like that. But when you see numbers standing in front of you, you start to notice patterns. And we're going to conjecture some things about those patterns. And the things we're going to conjecture, we're going to be able to write out theorems about. We're going to be able to say there's a really simple recurrence equation for the even cases and a really simple recurrence equation for the odd cases. And they don't give us these horrible substitutions. But how are we going to know if those things are true? We just guessed them because it looked like it. We're going to prove them by induction, which turns out to be a 3-line proof. We never would have discovered the theorem without writing down some data. We'd never be able to prove it from scratch. But we'll look at the data, discover these theorems, prove it by induction, work them back to get actual answers for the even and odd case, which will solve this general case that we otherwise would have been stumped by. So it connects to recurrence equations. It connects to induction. It connects to really why you want to use induction, because it helps you really prove things that you don't really see the big picture on. Prove things that you only understand what happens from one case to the next. And it's going to connect to this nice iterative generation of gray codes. And that connects to Hamiltonian circuits and hypercubes. So I really love this problem. I think this problem just knits everything together. Sums, graphs, recurrence equations, induction, and recursion. All right, that's where we're headed tomorrow. So solve this puzzle. If you solve it, then what I do tomorrow will make a lot more sense. If you don't solve it, it'll still make some sense. But try to solve it. All right.